جو آپ نے کورس آؤٹ لائن دی ہے اس میں تو لگتا ہی ہے کہ آپ اس کو فالو نہیں کر رہے. تو میں نے پھر ذرا غور کیا تو واقعی کورس آؤٹ لائن سے تو کافی ڈیویٹ کر گئے ہیں ہم. تو چلیں ٹھیک ہے، لیکن میرے لیے ایکچولی جو کورس آؤٹ لائن بنانے کے بعد اس کو فالو کرنا تھوڑا سا لرننگ ایکسپیرئنس کے ساتھ ہے کہ آپ لوگوں کے ساتھ ہم کون سی چیزیں زیادہ ایمفسائز کرنے کی ہیں، کس پہ زیادہ وقت لگانا ہے، اور کون سی چیزیں ایسی ہیں کہ ہم تیزی سے آگے بڑھ سکتے ہیں. کوئی سوال پوچھ رہا تھا؟ کون پوچھ رہا تھا؟ آپ پوچھ رہے تھے. ہاں یہ سوال جنہوں نے بھی کیا. نیکسٹ مڈ ٹرم کے اندر جو کورس کانٹینٹ ہوگا وہ پچھلے مڈ ٹرم کے کانٹینٹ سے آگے سے لے کر اس وقت تک جب تک کہ اگلا مڈ ٹرم ہوگا اس وقت تک کا کورس اس میں انکلوڈ ہوگا. ٹھیک ہے نا؟ یہ ہم نے ان پارٹس کر دیا تھا. اور اس کے بعد جو فائنل ایگزامینیشن ہوگا مڈ ٹرم کے بعد، اگلا مڈ ٹرم اس کے بعد ایک اور ہے، ایک اور مڈ ٹرم ہے، اور پھر جو فائنل ایگزام ہے وہ تمام کورس کو کور کرتا ہوا ہوگا. آلرائٹ. تو اس واسطے کورس جو وہاں پہ لکھا ہوا ہے آپ کے پاس اس میں کافی اس میں سے ویریشنز ہوں گی، ڈیویشنز ہوں گی، اور میں اس کو فی الحال آپ لوگوں جہاں جہاں جیسے جیسے مجھے ریئیکشنز یہاں پہ نظر آ رہے ہیں اس کے حساب سے میں موڈیفائی کرتا چلا جا رہا ہوں. کسی نے ایک اور نے سوال کیا کہ اب اس کے بعد ہم کیا کرنے والے ہیں پچھلے اگلے چند لیکچرز میں. میں بہت زیادہ لمبی مدت تک تو نہیں بتا سکتا، لیکن اگلے چند لیکچرز میں ابھی تو لاک تو نہیں کر رہی ہیں آپ؟
ایک کھلا ہے
ابھی تو وقت نہیں ہوا. اچھا چلیں. جو نیکسٹ فیو لیکچرز واٹ آر وی گوئنگ ٹو ڈو، میرا خیال میں سب سے امپورٹنٹ چیز جو ہے وہ یہ کہ اب جب ہم تھرموڈینامک ویریبلز کو آئیڈینٹیفائی کر چکے ہیں، وی شوڈ لرن ٹو فائنڈ ریلیشنز امنگ دم. And we should learn to manipulate these thermodynamic variables to get useful quantities out of them. This is what I am going to do in the next few lectures. I think this will be today's lecture as well as the next two lectures of the next week. So we were looking at the following thing. We were saying that thermodynamic variables we were able to identify volume, number of particles, pressure, temperature, internal energy, entropy. آکے جب آپ لوگ انٹر ہوں تو پلیز چپ چاپ بیٹھ جائیں، باتیں وغیرہ اب نہ کریں. These were various, and of course chemical potential, and perhaps, as I said, for different other systems we will have other variables coming in. I had identified also magnetization, magnetic field. I had identified electric polarization, electric field, and I had identified strains and stresses, etc., etc., etc. Various, depending on what kind of system one is dealing with. There is one very general classification which we did, extensive and intensive variables. In the last lecture, and we said that apart from these things, we will not consider them right now in the above, which is valid for what we said, fluid systems. extensive variables are N and V and U and S, and intensive variables are pressure and temperature and chemical potential. These are the variables that we have. And we noticed that a law like du equal to TdS minus PdV tells you immediately that temperature is partial differential of U with respect to V when you with respect to S when you hold volume constant, and that pressure is minus partial differential of U with respect to volume when you hold entropy constant. This followed very clearly by identifying U a function of S and V and writing du as partial differential of U with respect to S at constant volume times ds plus partial differential of U with respect to volume at constant entropy times dV. In a very standard way of writing differentials. Right? This was what we did in the last lecture. It is because of this and these two relations that we are able to identify these two quantities. And in fact, had we started with the very more general statement of mu times dN, then we would have obtained mu equal to partial differential of U with respect to N at constant S and V, and here then we would have put here constant N also. So the lesson is intensive variables are derivatives of energy function, are derivable from extensive variables. Right? This is a straightforward message that comes out of this exercise that we did in the last lecture. And therefore, if we were to ever have an equation relating extensive quantities, extensive variables, we would be very happy. Because from that relationship we would be able to get all the intensive variables also. Therefore, then we will have a complete set of all the variables that we need to do thermodynamics. And this equation that relates extensive variables is, in the last lecture we said that this is called the fundamental equation. And it is called the fundamental equation for this purpose, that knowing this we would be able to get all the intensive variables and all the set of variables that we need to do thermodynamics. Yeah.
Sir, could you repeat what you said about energy in the case of intensive?
Would I repeat what I said about the energy? What did I say about the energy?
I think you said something about energy function. I'm not sure, but I think you said something about energy function.
Don't ask me what I said, okay? Ask me to repeat what. किसी को मालूम है क्या कह रहे हैं? ये कह रहे हैं कि कोई एनर्जी फंक्शन की मैंने बात की. कौन सी एनर्जी फंक्शन की मैंने बात की थी?
इंटेंसिव या एक्सटेंसिव की बात कर रहे हैं. इंटेंसिव वेरिएबल्स आर डेरिवेटिव ऑफ एनर्जी.
ओके. बट लेकिन जिसको देखें ना, इंटेंसिव वेरिएबल्स डेराइवेबल फ्रॉम एक्सटेंसिव वेरिएबल्स. Now, the derivatives are all of the energy function. And I think I will get to talk of energy functions in a minute. So hold on there, right? In today's lecture, we will talk of various other energy functions also. Okay? So, and we will derive them also. But I want to emphasize over here that there is this equation called fundamental equation. And if you have support, you can visualize it in the following manner. You can say that there is this space, three-dimensional space of, in this particular example that we have, of S and U and V, these three extensive variables. The fourth one we, for the moment, do not include. Then an equation among these variables amounts to describing a surface in this space. Right? A surface, there will be points that will be I can imagine this surface to be something like, something like this. And this surface will whatever my poor drawing is able to tell you, there is a surface in this, and this surface describes point by point relations among the three variables S, U and V. Okay? And this surface is what we call fundamental equation. But an equation is important because given that equation we will be able to get all the intensive variables, and I have a very good example over here to take. Somebody tells us that there is a relationship for an ideal gas. Somebody says that, and we sort of are trying to now verify if that statement is correct or not. So someone says, look, for an ideal gas, entropy is equal to n times the Boltzmann constant times log of V over n times 4 pi m times internal energy U divided by 3 times h times h, n times h squared, and closure of the square bracket also, plus 5 by 2, and the curly bracket is also closed. Someone says, I have worked very hard to get this relationship for an ideal gas. And clearly this relationship is, and there will come a time when those of you who do statistical mechanics will be able to actually derive this equation for yourself. There will be, we will not have time to derive this in this course because this is not a course on statistical mechanics, but some of you will learn statistical mechanics in future and will derive such an equation. This is a fundamental equation. And here there are many constants. So let me write this as n times k times log of v over n times u over n to the power, oh, there is a power over here, sorry, 3 by 2. I'm sorry, there is a power 3 by 2 over here. To the power 3 by 2, and then I will have plus 3 by 2 k times n times 5 over 3 plus log of 4 pi m over 3 h squared. So those of you who do not trust that this is the same as this can sit down and do a little bit of algebra for yourself. Okay? What I've done over here is that I will assume n to be constant here, as if it is not an open system. The system is not exchanging material with the surroundings. And I am over here, therefore, put everything which is constant in the last term over here, so that I can say that entropy is the relationship that I have is n times k times log of v over n times u over n to the power 3 by 2 plus S naught. S naught is some constant term that defines S naught and now, this is a simplified form of that same fundamental equation given by somebody else. What I will do is that I will apply these relations that exist over here and try to work through these to calculate temperature and pressure. Okay? And calculating temperature and pressure, we would get to know if truly this equation represents an ideal gas or not. Because we know the relationship between temperature and pressure of an ideal gas, PV equal to nKT. We should be able to get that relationship over here. So this is what we are going to do over here, and you will agree with me that I can take this S naught onto that side, S minus S naught, and I can divide by nk, and then I can take, so I will have S minus S naught over nk is equal to log of this quantity and log of v over n u over n to the power 3 by 2, and therefore v over n v over n times u over n to the power 3 by 2 is equal to exponential of S minus S naught over nk. Right? Is everybody with me? Okay. And I can therefore take u over n to the power 3 by 2 equal to n over v exponential of S minus S naught over nk, and we are getting there now. I can take to the power 2/3 on this side, so I will have 2/3 on this side, and I can have 2/3 over here. Okay, I just this was to the power 3 by 2, and I took 2/3 of that and to the power 2/3, and I just transferred this power 2/3 in this manner. And this allows me to write u as equal to n times n over v to the power 2/3 times exponential of 2 over 3 S minus S naught over nk. Okay, are my letters getting too short, too small for people on the back side? Okay. Now, this is a shape in which I can now take derivatives. Okay? So, temperature. Temperature is du by ds at constant volume and n. So, volume and n are to be held constant, and I can take temperature as du by partial differential of u with respect to s, and I keep v and n constant. Right? This is how temperature is defined, and that will be equal to n times n over v to the power 2/3 times the exponential differential of exponential is the exponential itself, and then I will have 2 over 3 times n times k is what I will get, times exponential of 2 over 3 S minus S naught over Nk. Are you all with me? Right? So I can quickly identify n times this times exponential as u. So I have therefore 2 over 3 Nk times u. Okay? Straight away, because this times exponential is u. So this times exponential is u. So I get an equation u equal to 3 by 2 nkt. Here you are, an equation for ideal gas. Ideal gas has said, in ideal gas, internal energy is equal to 3 by 2 nkt. Wonderful. We got an expression for temperature, but the expression for temperature is equal to this. How about the other one? So we take P. P is equal to minus du by dv at constant entropy and number, and we can do this algebra a little bit, and we will, should I do this over here, or I'll leave it to you, because it's a very straightforward, simple thing to do. You will end up by seeing clearly that P is equal to nkt over V. The equation that you know is the one that describes ideal gas. I didn't do it over here, just save some minutes for myself. And so a fundamental equation is important in the sense that once you know it, then you can work out other intensive variables also. And once you know all the variables, then you know the relations, you know equation of a state, and from the equation of a state you can work out many other properties and so on and so forth. How would one have derived this expression? Actually, this expression is derived from S equal to K log omega. And this expression, or from minus K times sum over I pi log pi. In statistical mechanics, the importance of these relations is that if you use microscopic details of the system and work through and work out these expressions, any one of these, whichever is convenient, and you will get a relationship like this, and that relationship will then open up entire thermodynamics for you. Okay? So whenever somebody gets an expression like this, he says, oh yes, now I can do my thermodynamics, because then everything else is just straightforward from there on.
ये क्वेश्चन ऐसे कोई के नेचुरल लॉग से निकली है तो वो नहीं होगी फंडामेंटल इक्वेशन.
Okay, so the question he is asking is, if this equation has come out of this equation, should we call this the fundamental equation? So yes, you are right. We should call this the most fundamental equation. But my point is that in thermodynamics, this equation is at the border between thermodynamics and statistical mechanics. So you do some conceptual work in statistical mechanics, and then you use this equation and arrive at some expression which will give you this. But when you are in the domain of thermodynamics, then you start from here, or whatever equation somebody works out and gives to you, you can work out all thermodynamics from it. Okay? So this is a great thing, and of these you can, we have seen that, intensive variables, extensive variables are, among the extensive variables, U and S are not directly measurable in the laboratory, right? U and S are not directly measurable. Whereas volume and pressure and temperature, these are directly measurable quantities. So equation of state, which is what this is, usually deals with these numbers. In fact, N is also something which is directly measurable in terms of number of moles that you consider from masses and from other things you can work out N. So N can be fixed experimentally, T and V and P can be fixed. So equation of state and fundamental equation are different in this respect. The fundamental equation is in terms of some of the variables which are not determinable in laboratory, whereas equation of state is all in terms of variables which are directly measurable in laboratories. Okay? Good. Now, let us go back to that equation du equal to TdS minus PdV, and we said u is a function of S and V, and therefore we said that this is the same as TdS minus PdV as we wrote up there. Okay? I could write this fundamental equation in a slightly different form. I could write entropy as a function of U and V. Then our ds would have been partial differential of S with respect to U at constant V plus partial differential of S with respect to V at constant U. Okay? Oh, I'm sorry. Multiplied by du and multiplied by dV. All right? Now, you know that ds by du by ds at constant V is temperature, and you know the algebra, so ds by du at constant V will be 1 over T. Okay? Times du, and ds by dV at constant U, what will this be? We will need to work it out. ds by dV at constant U, I should be able to write it using the cyclic principle, you know, the cyclic principle that I wrote yesterday. Let me repeat that. dx by dy at constant z multiplied by dz dy by dz at constant x multiplied by dz by dx at constant y is equal to minus 1. This is a fundamental identity in differential algebra. And therefore, from there, one can immediately see that dx by dy at constant z will be equal to, I can take things on that side. If I take this thing on that side, invert it, it will become dz by dy at constant x. And I take this quantity in the denominator, I will get dz by dx at constant y. Okay? Minus sign also, yes. With this, then I can write ds by dv at constant u as minus partial differential of u with respect to v at constant s and partial differential of u with respect to s at constant v. And there I have the desired intensive variables. du by dv at constant s with the negative sign is p, and du by ds at constant V is temperature. So this quantity happens to be P over T. So I can write here P over T times dV. Okay? Am I going too fast? हाँ? अच्छा
सर ये जो आपने ये वाला स्टेप है जिसमें आप दो टर्म्स इस तरफ ले गए राइट हैंड साइड पे, इसमें तो हम ऑपोजिट भी तो कर सकते
थे
सर, तो वहाँ हमारे पास P by P
नहीं आता, फिर भी नहीं आता.
हम ये रिलेशन सिर्फ यूज कर रहे हैं.
You can do it whichever way you want to do it. It will come out to be P over T. You know, it doesn't matter how you take them on the other side. They would have been inverse of this and inverse of this. 1 over P and 1 over T will have come out to be P over T. Okay? So now you have copied everything that I've written over here. So I can move on now. So the relationship is this, and from here I notice immediately that this is the same as du equal to TdS minus PdV. It is the same law. This equation is the same as this, as it was that. कहाँ गई वो? Here. As it was here. du equal to this. So, whether I start with this or with this, or even with V as a function of U and S. एक मिनट. V as a function of U and S, I will get exactly the same equation, yes.
सेम माइनस P by T क्यों नहीं होना चाहिए, नहीं समझ में.
माइनस P over T क्यों आया? ये तो यहाँ से इन दोनों इक्वेशंस है. Numerator is du by dv at constant S, which is equal to minus P, and denominator is du by ds at constant T, which is equal constant V, which is equal to T. Huh? Okay. So the last comment that I was making over here is whether you take the fundamental equation as U a function of S and V, or S a function of U and V, or V as a function of U and S, you will end up with the same differential, the equation du equal to TdS minus PdV. I have not shown this here, but I leave it to you to show. Okay? You will see for yourself that the way this equation translates into exactly this equation, similarly this functional form will translate itself into exactly this equation. So a fundamental relationship between U, S and V has exactly the same form when you write in the differential form like this. Okay. Right, now I am coming to defining some more energy functions. All right. You know that I'm now taking you back to very old times when we used to write du as dw plus dq. In ancient times we used to write this way, the first law of thermodynamics. And we said that du is such that it is and dw was minus pdv, so that if I have a constant volume process, then in the constant volume process dw is equal to 0, and therefore du is the same as dq, and we will write over here small v to show that this is in the constant volume process. And then we can integrate the two sides from state A to state B, state A to state B, and what we show over here is that this is equal to some total heat that has been exchanged between the system and the heat reservoir under constant volume conditions. So the conclusion that I derive from this is, under the condition of constant volume, the heat exchanged, the exchange heat goes entirely into changing internal energy. Okay? Constant volume process, whatever heat enters the system goes into increasing the internal energy of the system. Whatever heat leaves the system is at the expense of internal energy of the system, if the process is constant volume process. Okay? We want to check this system out also for a constant pressure process. In the constant pressure process, you won't be able to make this statement at all. And integral du a to b will be equal to integral a to b, and it will be dw plus dq. And won't be that simple. Will not be that simple. And that actually leads us to defining a different energy function. For which we can make a statement similar to this, that under constant pressure the exchange heat goes entirely into changing that energy function. Okay? We will call that energy function H. And we notice that if we define it as U plus PV, if we just define it U plus PV, then dH is du plus pdv plus vdp. All right? Yeah. नहीं, हमने propose किया. We are proposing a new energy function H, which is U plus PV. Okay? And we have to see what we conclude out of this. All right? Yeah.
Different energy functions you define for us.
Oh, why are we defining this new energy function? I'll explain that in a minute. I think मेरा ख्याल है मैंने कहा भी था. यहाँ पे हम ये कह रहे हैं, under constant volume, the exchanged heat goes entirely into changing internal energy. हमारा ये ख्याल है कि one can define an energy function for which we can make the following statement: under constant pressure, the exchanged heat goes entirely into changing that energy. So that will be an energy which will be what the change will be about under constant conditions of constant pressure. And that is very significant, very important for us, because everything that happens around us actually happens under constant pressure, doesn't it? Whatever work we do, whatever chemical reactions take place, whatever grows out, or all of those things that happen around us happen completely under constant pressure, don't they? So constant pressure, therefore, is a very important thing. And under those conditions of constant pressure, if you can find that energy function to which all the energy goes into or comes out, then we should be then talking about that energy function, right? So this is the reason why we are going after. And this is not the only energy function. There will be other energy functions also, and we will go after them, after this. So we have therefore dH defined as du plus pdv plus vdp, and I can write this du as tds minus pdv, and I can then add write this other terms, right? I can write the other terms, and I will notice that I can. No, I will do the following. I'm sorry. I will do the following. I will write du not as this, but I will do it in the following form. I will say du is dq plus dw. And for the purpose of explaining my logic, I'll say, therefore rewrite this whole statement. I have written dH is equal to dq plus dw plus pdv plus vdp. Okay? And now if I take dw as vdp as pdv, so minus pdv, so I will have dq minus pdv plus pdv plus vdp. Then I have these two terms cancelling out, and what is left is dq plus vdp. All right? No magic, just manipulation of those variables and those equations. And I get therefore dH equal to dq plus vdp, and therefore change in this energy function h from A to B, which will be HB minus HA, will be equal to change in the heat that is transferred in the process A to B, plus something which happens over here. And if I say that this is VdP from A to B, and if this happens under constant pressure, HB minus HA is equal to Q only. All right? So what I have been able to get over here is an energy function for which I can write that statement. Under constant pressure, the exchanged heat goes entirely into changing this new function. This new function H is called enthalpy. Okay, this new function is called enthalpy. And therefore, under conditions of constant pressure, whatever heat goes into the system or comes out of the system goes into changing the enthalpy of the system. All right? So if we are working in an open environment under constant pressure, like jumping up and down and doing some work over here, you actually are changing enthalpy of your own enthalpy, because your body is exchanging heat from the outside and inside under constant pressure, and the change is happening not in the internal energy but in enthalpy. All right? Now, the transformation that we performed over here, which gave from U to H happened under a transformation which we said H is equal to U plus PV. As simple as that. We said the transformation is H is equal to U plus PV. And this transformation is called Legendre transformation. Okay? So a big name, Legendre transformation, but when it comes out, it is only a transformation of this kind. And this is more general. This allows us to look at it in a more general way than what is visible so far. And that more general way is when we say that, look, if I have a function, I can say the following. I can say that, look, from U, U was a function of S and V, and here I have an H function, a new function, which is, I haven't changed it over here, S and P. I haven't shown that yet, okay? DH will be this. And this transformation that I have yet to describe actually takes you from a dependence on one variable to the other variable. So let me get to the describing the transformation in some detail. All right, the other thing, before I forget, I should also point out, when I write down an expression like this, or for U and for this, I can write, because under conditions of constant volume, heat goes entirely into changing internal energy. Therefore, heat capacity at constant volume is partial differential of U with respect to T at constant volume. Okay? And because under constant pressure, all the heat goes into changing the enthalpy function. Therefore, under constant pressure, all the heat goes into changing the enthalpy function, and therefore heat capacity at constant pressure is this. Okay? Heat capacity at constant pressure is this. And there is another definition of heat capacity. Heat capacity is usually written as T times partial differential of S with respect to T at constant V, and heat capacity at constant pressure is written as T times partial differential of S with respect to T at constant pressure. These are other ways of writing heat capacity. And you can easily verify that this means the same thing as this, and that this means the same thing as this. You can easily verify. All right. I will go to now defining the Legendre transformation. And once we define this transformation properly, then we will be able to define other energy functions also. And this is what we should be doing, so that the whole variables, whole set of variables that go into defining thermodynamics just is there for us. Let me try to show Legendre transformation in a more general form. In a more general form, in the following sense, I can say that if f is a function of x and y, then you know that I can write df as partial differential of f with respect to x at constant y times dx, plus partial differential of f with respect to y at constant x times dy. This is something that we have done so many times that we know it by heart. I can write df, I can write a as df by dx at constant y, and I can write b as df by dy at constant x, which means I can write df as a times dx plus b times dy. No big deal. This is all pretty simple, straightforward. I can, compared to that, I can define a function g, a new function, which I propose is a function of x like f, but rather than being a function of y, it is a function of b. b is df by dy. b is df by dy. Okay? And if I propose it to be so, then I know that this amounts to saying that dg will be equal to partial differential of g with respect to x at constant b dx plus partial differential of g with respect to b at constant x db. Right? If it is this, then this is straightforward from there. I can achieve this by writing g as equal to f minus b times y. Nearly the same manner in which we did over there. We wrote u plus pv, and for some reason pv disappeared and vdp remained. Okay? So we are writing this then f minus b times y, so that if I were to write dg here, I will say it is equal to df minus b times dy minus y times db. Okay? And I can also write for df now, df as a times dx plus b times dy minus b times dy minus y times db, and this b times dy, b times dy cancel out, and what I am left with is a times dx minus y times db. See, here, through this transformation, I have ensured that change in g is brought about by changes in b and x. right? Like changes in f were brought about by changes in x and y. So changes in x and y brought about changes in f. And through this transformation, I have shown that changes in g are brought about by changes in x and b. Okay? Which means that I have shown that g is a function of x and b. And this was achieved by simple transformation like this. Okay? And this transformation actually is equal to f minus y times df by dy at constant x. Right? As simple as that. So this is how this transformation goes, and this is precisely what we did over there. If you go back to our derivation over there, हमने क्यों किया? हाँ एक okay, x, the function f depended upon x and y. We have defined a function g which depends upon x but not y, but f prime, which is f prime. dy by df by dy at constant x. This is what we defined b, right? Depends upon that. तो इसकी जो सिग्निफिकेंस अब इसमें नजर आएगी आपको. मैं अभी एक मिनट में ये थर्मोडायनामिक्स में इसकी सिग्निफिकेंस क्या है वो मैं आपको भी बताता हूँ. वहां से go back to that expression over there, h is equal to u plus pv. So we had du equal to tds minus pdv, और इसमें change in u was brought about by change in entropy and change in volume. We make a transformation and we define h as u plus p times v, so that dh is equal to du plus p times dv plus v times dp, and we substitute for du from here, so it is t times ds minus p times dv plus p times dv plus v times dp. All right? And these two things cancel out and we get t times ds plus v times dp. So change in h depends upon change in entropy and pressure. Okay? Change in u dependent upon change in entropy and change in volume. Change in enthalpy depends upon change in entropy and change in pressure. Okay? So there is this dependence on variables because of which some energy functions are defined otherwise. But the physical significance is already expressed over there. That whatever heat appears under constant pressure goes into nothing but changing the enthalpy of the system. Okay? Or the constant volume process going into changing the entropy of the system. All right. So here we have therefore defined a new function for which there is a new in addition to this expression, now we have an additional expression over here. All right? And this starts to give us ideas. And we can go on defining other variables and other functions, and we will actually can define two more functions. suppose we wanted to, U is a function of S and V. So we went from here to defining H, which is a function of S and P. How about going from here and defining another function, let's call it F, which is a function of not S but T and V. And how about defining a function from here, which is, we call it G, a function of T and P. Okay? So it sort of gives us ideas, and we start to think about defining two more energy functions. Two more energy functions. We had started off with one, and we got this one, and we think following the same procedure we can get this and we can get this. Alright? And these will be good enough energy functions. We can write Lejeune transforms for them, and the transformation will be such that from U, S and T product will be different. You see, I also need to tell you something else over here. I think I should spend a couple of minutes to explain something that I have not explained yet. A very special relationship that exists between these 4 or 6 parameters. I think I did yesterday in my last lecture. T times S dimensionally is energy, as is P times V, as is mu times N. Right? As is, one square bracket means dimension wise. Okay? Dimensionally, they all have dimensions of energy. And as will be magnetic field multiplied by change in magnetization. As would be stress. Let me call it stress sigma and strain dE. So, sorry, I shouldn't put dE over here. These two variables have a kind of relationship with each other that together they define an energy function. Okay? Yesterday, in the last lecture, I defined works of different kinds, magnetic work and elastic work and chemical work and mechanical work and so on, and thermal work, energy. So all of this energy and work were actually, dimensions of energy. So these combinations are dimensions, and therefore we should be thinking of taking these variables in pairs, because together they give the correct dimensions of energy. And therefore I will say that T and S set are conjugate variables. Similarly, I can say P and V are conjugate variables, and I can take, say, mu and N or H and M are conjugate variables. These are conjugate variables. And they are conjugate variables also because one can be always found as derivative of some energy function with respect to the other. But we will in the next couple of lectures, we will see the significance of these variables being conjugate variables in a number of situations. So even if you are a little disturbed on this thing coming out of nothing, you should understand that this is going to come up before us in several different ways in the coming lectures. So I'm coming back now to going back to this particular point, which was about defining other energy functions. And I said that you see, change that took place from going from U to H was in conjugate variables, V to P, right? V and P are conjugate variables. So the change that took place is from a variable to its conjugate variables. And this is because, as I sort of erased over here many of those relations, P is a derivative of U with respect to V, okay, and so on. We will come to those relations later on. Similarly, we can think of going from U to F, this function F, because we go from changing one conjugate variable to another conjugate variable as independent variables, S to T. Similarly, over here we go by changing S to its conjugate variable T in this manner over here. Similarly, we could think of this being a Legendre transform of this by changing V to P in this manner, and so on. So I am therefore, having defined these conjugate variables, I will go on to applying Legendre transforms to F, defining F as U minus Ts, so that dF is du minus T times ds minus S times dt, and writing U as TdS minus PdV, and then minus TdS from here and minus SDT from here, and these two terms cancelling out, and you are left with minus PdV minus SDT. So F therefore is an energy function such that a change in this function comes about because of change in volume and temperature. Right? Change in F is caused by change in volume and temperature. Okay? And I can similarly write G function as H plus PV, so that I have dG as dH plus P times dV plus V times dP, and dH I can write from somewhere over there, dH as TdS plus VdP. Did I make a mistake? Huh? Where did I make this mistake over here? Minus PV hoga na ye? Yes. So I will need to take this minus PV, okay? S and T कौन सवाल कर रहा था ये? या क्या कर रहे थे? इसमें यहाँ पे हम U was a function of S and V, and from here by making this transformation we went to a function F, which is a function of T and V. So the role of S and T was interchanged. Is that T or
S को H to G
G में? No. H is a function of, did I write it wrongly? No. H is a function of S and P, and this is S and T. Oh, change in S and T, you are right. Okay. अच्छा, ये अच्छा याद दिलाया Okay, we are changing S and T, so I was making a wrong transformation over here. So I'm glad you are here to catch my mistake. So this is dH minus TdS minus SdT, and dH is TdS plus VdP minus TdS minus SdT, and these two terms cancel out and you are left with VdP minus SdT. Okay, now this function F is called Helmholtz free energy. Helmholtz free energy or thermodynamic potential, Helmholtz thermodynamic potential. This energy G is called Gibbs free energy. We have therefore four energy functions: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Four energy functions.
आप जिसको ट्रांसफॉर्मेशन करते हो आप एक्सप्लेन कर सकते हैं क्या लॉजिक यूज करते हैं कि कौन सी ट्रांसफॉर्मेशन यूज करती है?
ओके, पहली बात तो ये कि उन्होंने पकड़ ली मेरी गलती ना, क्योंकि उन्हें मालूम है कि क्या ट्रांसफॉर्मेशन में होनी चाहिए थी लॉजिक, एंड आई थॉट दैट विल एक्सप्लेन टू यू कि क्या होना चाहिए. इफ आई एम मेकिंग दिस ट्रांसफॉर्मेशन एस एंड टी, आई विल सबट्रैक्ट एस एंड टी, टी टाइम्स एस. इफ आई एम मेकिंग दिस ट्रांसफॉर्मेशन P and V, because P के साथ एक नेगेटिव साइन होती है, so I will add P times V in the transformation. So wherever I made a transformation with P and V, I added P and V, and I could actually, you know, अच्छा ये ट्रांसफॉर्मेशन जो है ना, इसके बारे में आप इस मैप से ये समझें कि इस मैप से कि H is a transform of U, F is a transform of U, but conversely U is a transform of H, and U is a transform of F, and G is a transform of F as well as H, and you can actually think of G being a transform of U also, or U being a transform of G. So actually all four energy functions are transforms of each other. Transforms of each other in terms of independent variables. Okay? So if I were to start not by knowing A, U, H, F and other G, and I say there is a function called A, which is a function of X and Y and Z are conjugate variables, and I want to get to a function B, which is a function of X and Z. Y and Z are conjugate variables. If they have that relationship, then I will define B as A minus Y times Z. And it will automatically come out that yes, B defined that way will have this property. I can also define a function C. Suppose x, y, z, and there is a function, there is a variable I will call. We have used up so many variables. I am left with V. No, V is used up, and U is used up, and T is used up, and J. Brilliant idea. So we can define a function C, which is a function of J and Y. Okay? C as a function of J and Y, and J and X being conjugate variables. Then I can write C as A minus X times J. I can also write I can also write C as B say transformation B minus xj minus zy. I can make this transformation from B to C also. Okay? And what I wrote over here is most general, which gives you a picture of how this transformation is taking place and how you can go about making these transformations. So I can define this C in terms of B and write this with changing x by j and z by y in this manner, both of them. Now that amounts to saying that I could get G from U. I could write G as equal to U minus Ts plus PV. Okay? And this is very obvious that this energy function, we have therefore energy U, energy E as U plus PV, and energy F, which is U minus Ts, and energy G, which is U minus Ts plus PV. We have these energy functions in this particular form. Okay? And you can write this also as G, can write this as F plus PV. You can write it as H minus Ts, the way we did over there. ठीक है ना? I can write G in this form, either that way or this way. Okay? So, therefore, there are these energy functions: Helmholtz free energy or Helmholtz thermodynamic potential, and Gibbs thermodynamic potential, and then enthalpy and internal energy that has been with us from that time on. Thank you very much. Any more questions?